So I want to make one point here that we defined infinite set earlier. However, we actually have a relatively simple alternative characterization of an infinite set that helps us kind of understand the meaning of infinity or an infinite set, regardless of whether it's a countably infinite or an uncountably infinite set. And this is that a set S is infinite if and only if it is in bijection with a proper subset of itself. And this is a relatively simple theorem, so I'm going to omit the proof of this, but it comes straight from the contrapositive of our previous definition of finite set. So it's a good idea for you to check this, try and go through and prove this yourself, but I'll just give two examples to kind of help out a little bit. Instead of all integers, 0, plus or minus 1, plus or minus 2, and so on and so forth, is infinite because it is in bijection, or set theoretically isomorphic to the set of even integers, 2z. And we define the set of even integers as just all integers that are divided by 2, or divisible by 2. It's clear that the even integers are a proper subset of z, and yet if we define the function g from z to 2z such that g of p is equal to 2 times p, g is a bijective function. So this property characterizes the fact that a set of all integers is an infinite set because it has the same cardinality as a proper subset of itself. For an uncountable example, and we'll prove why the real numbers are uncountable in this lecture, but take the open interval of real numbers from 0 to 1, so this is the real number line, all positive real numbers from 0 to 1. This is clearly a proper subset of the set of all real numbers, and yet later on in this lecture we'll show that, and we'll mention that the function from this open interval from 0 to 1 into R is defined by g of x is equal to 2x minus 1 over x times one minus x is a bijection from the interval from 0 to 1 in R. And remember, this is not ordered pair right here. This is we have a very distinctive meaning, and it could possibly cause some confusion, but this means the set of x in R such that, a set of real numbers such that x is less than b and greater than a. Whereas this notation means the set of all real numbers x such that a is less than or equal to x, which is strictly less than b, this means the set of all real numbers such that a is strictly less than x, and x is less than or equal to b. And lastly, this means the set of all x in R such that x is greater than or equal to a, and x is less than or equal to b. This is sometimes called interval notation. And will be familiar if you've taken a calculus class, but it's important to not confuse this interval notation with ordered pairs that we introduced before. So typically in a given construct, you'll be very specific to mention whether you're using ordered pairs or if you're using intervals of real numbers. But very often when you're reading, it's evident based on the context of what you're reading. Continuing on, what I want to do is introduce a very useful concept between sets, which is called the, specifically functions, which is called the composition of functions. So we define the following. If f is a function from a to b, and g is a function from b to c, then the composition of function g with function f is denoted g circle f of x, and it's defined by g, the function acting on f of x. And this is a new function from a into c. This is a very useful operation for a number of different reasons. One of the big reasons is that has to do with how it interacts with the properties that we've talked about so far for functions. So injectivity, surjectivity, and lastly bijectivity. But just for example, let's say we take two functions, take f, where f is the factorial function that we defined before, and we take the function g, to be the function n squared. In this case, f composed with g of n is going to be f of g of n, which is going to be the factorial of n squared, and g composed with f of n is going to be g of f of n, which is going to be n factorial squared. And looking at our definition before, it's not always going to be possible to form the reverse composition, but it is possible in this case because the sets A, B, and C are all the same set. And this also points out, this example also points out the fundamental point here is that the order, if we can do switch composition or change the order of a composition, we get a different function in general. So in this case, f composed with g of 2 is going to be 2 squared factorial, which will be 4 factorial, or 24, while g composed with f of 2 is going to be 2 factorial, which is just 2 squared, which itself is equal to 4. So the order of a composition is very, very important. Even if the sets A, B, and C are the same. But in general, right, we have to be very careful what the domain and codomain is of each one of these functions. So we have 2 theorems, both very important. The first one is the composition of 2 injective functions is also injective. This can be proved directly, so we consider x1 and x2 in the domain set A such that g composed with f of x1 is equal to g composed with f of x2. This is saying that g of f of x1 is equal to g of f of x2, and then if we assume that g is injective, so we're assuming that f and g are both injective, by the injectivity of g, we have to have that f of x1 is equal to f of x2. And furthermore, by the injectivity of f, if f of x1 equals f of x2, then x1 has to equal x2. Therefore, g composed with f is an injective function. Which is very neat. By a similar argument, we can say that the composition of 2 surjective functions is also surjective. And the proof of this proceeds very similar. So we assume that f and g are surjective. Then we take an arbitrary element y in C. And then by the surjectivity of G, there exists some B element in the set B such that Y is equal to G of B, so that's what the surjectivity of G is, what guarantees the existence of this B. And furthermore, by surjectivity of the function f, there exists some x in A such that B is equal to f of x. So this means that for arbitrary y, in C, there exists an x in A such that G composed with f of x is equal to y. This is evidenced because by the fact that G composed with f is G composed with f of x. F of x is B, and we know that G of B is equal to y, which concludes the proof. And what's neat here now is that the corollary that we have here is that it doesn't really require any proof at all. You could write down a very short one-line proof, but this is that the composition of two bijective functions is also bijective. And this is really important, because what this means is that sometimes in mathematics we want to prove something about a certain set of objects. We need to take a number of different steps to make a proof and prove a certain property about a given set of objects. And let's say it's just a cardinality proof. We're proving something about the cardinality of a certain set of numbers. If I can establish a sequence of bijections to get from, say, set A to set D, and I prove something nice about set A, and I can find bijections all the way to set D, then I've effectively proven things about set D. This is a huge idea in mathematics, which is why this is so important, and the concept of set theoretic isomorphism is so important. For example, we defined this idea of countable versus uncountable sets, and what we're going to be able to show is that, and we've already defined, a countable set is any set that is set theoretically isomorphic to the natural numbers, or there exists a bijection from the natural numbers to that set. We can immediately show that the integers are set theoretically isomorphic to the natural numbers, and something we will show, which is a little bit more complicated to show, is that the integers, or the natural numbers, are set theoretically isomorphic to the set of all rational numbers. So, believe it or not, the set of all rational numbers is a countable set. And we will prove this a little bit later on. If there are countable sets, there are also uncountable sets. The best example of an uncountable set that you're probably familiar with is the set of all real numbers. So we'll be able to show that this the set of all real numbers is actually uncountable. We'll prove this a little bit later on. We'll also show that this is set theoretically isomorphic in bijection with the interval from 0 to 1. So this is not the ordered pair 0, 1. This is important. There's interval notation that you'd be familiar with if you took a calculus class. This is the open interval of all real numbers from 0 to 1, and not the ordered pair 0, 1. But as it turns out, we'll also be able to show that this, and I'm not going to show this explicitly, but I will mention how to show it. This interval is set theoretically isomorphic to the power set of the natural numbers. And what I will prove momentarily is that any set is strictly smaller than its power set. It always has a strictly less cardinality than its power set. So this is the reason why the real numbers, in some sense, are so much bigger than any countable set. So many of these bijections, or set theoretic isomorphisms, are not trivial to show. So we're going to spend a little time constructing some of these. I won't be constructing this one. However, it's relatively straightforward to do and to show that it's set theoretically isomorphic with the use of what's called the Cantor-Schroeder-Bernstein theorem that I will write down and show in lecture today. But some of these results are a little bit non-trivial and a little bit hard to see at first, especially because the set of rational numbers is actually has this property of what's called density, which is a topological property, and it's dense in the real numbers. So I'm not going to get into what the definition of density is. You see that in a more advanced real analysis course or in a topology course. But the idea here is that if we take the real numbers, the real number line, right, around or surrounding any real number, say the square root of 2 is a real number and we proved that it's not rational, we can get as close as we want to the square root of 2. And this is true with rational numbers. And this is true for any real numbers. The real numbers are essentially, the real number line is essentially littered with these rational numbers, right? 1/2, 1/4, 1/8, around any real number you can get as close as you want and surround it with two rational numbers. This is the mathematical idea behind the definition of density in a topological space. Typically in discrete math, we are going to be considering sets that are not dense in the real numbers. However, it's this, you have this density property, and it's surprising in some sense, and it's kind of confusing to a lot of introductory mathematicians that in terms of the cardinality, even though the rational numbers are dense in the real numbers, the set has the same cardinality as the natural numbers. So in some sense, it's a much smaller set than the real numbers are. So this is a very, very interesting example. But the idea here is that, and specifically behind this corollary, is that if I can find bijections from set to set to set to set, if I prove one thing about one set, those bijections help me prove things about additional sets that I can biject to my original set. The first real theorem that is important to state is the theorem that if A and B are countable sets, then A union B is also countable. Note that this means, by the contrapositive, right, if you have an if P then Q, this is logically equivalent to a not P or not Q then P, and then not P, if the union of two sets is uncountable or not countable, then the negation of A is countable and B is countable is A is not countable or A is uncountable, or B is uncountable. And this proof is done in the book, so I'm not going to go through and do it right here. It's a relatively simple proof by cases. So I recommend you take a look at that and you understand it when you're going through and reading this chapter. So what I want to do right now is go through and show some of these bijections, okay, and show that it's relatively straightforward for certain sets to go through and show this countability versus uncountability. So we'll start off by showing that the set of all rational numbers is a countable set. And the idea here is the following, right? We have to show that there exists a bijection between the set of all rational numbers and the natural numbers n. Which means that we need to be able to find a mapping that's both injective and onto, or injective and surjective. And recall that we've defined the rational numbers as a set of all ratios P over Q, such that P is an element of Z, or an integer, and Q is a non-zero positive integer. And we'll just take this listing and we'll try and list out, right, all of the possible rational numbers. We can do this as follows. That's every rational number divided by 1. And this listing is only showing the positive rational numbers, but we can do the same thing with the negatives. And take the union of the two sets to use the previous theorem. to note that there are definitely other ways of approaching this proof. However, this is the simplest method that I like going over in my introductory discrete mathematics course. So, take the function g from the natural numbers into the integers, or the rational numbers, q. We'll say that g of 0 is this, g of 2 is this, g of 3 is this, and so on and so forth. And you can see that if we do this procedure ad infimum, so we continue to do this, we will have successfully enumerated every possible fraction, or every possible rational number in the integers, or in the rational numbers with the integers, and this concludes, right, that the cardinality of the rational numbers is the same as the natural numbers. And the reason this works is sometimes seen as counterintuitive, but the idea here is the analogy that Hilbert used is what's called Hilbert's finite hotel versus Hilbert's infinite hotel. If you have a finite hotel with a finite number of rooms, there's always going to be a point at which you run out of rooms for people to stay in the hotel. So in this picture that I've drawn right here, you have 4 rooms. Once all of the rooms are occupied, you've run out of rooms in the hotel. However, if you can imagine an infinite hotel with an infinite number of rooms, you never exhaust the supply of rooms. So you can continuously just keep adding guests to room after room after room after room after room. This is a good analogy. And like I said, there are other bijections, right? But this is probably the simplest way of explaining why the set of all rational numbers is countable. To show that the set of all real numbers is uncountable, we have to do a little bit more work. And in the following, we're going to use this notation to denote the open interval of real numbers between 0 and 1, or if you think of the number line, instead of all real numbers in between 0 and 1. So we can show that the interval from 0 to 1 is in bijection with the set of all real numbers. Relatively straightforward to do this. And you can consider the function to prove this. From 0, 1 to r, specifically defined by 2x minus 1 over x times 1 minus x. And it'd be a good exercise for you to prove, so I'm going to leave it up to you, but this function can be shown to be both injective and surjective. Be a good exercise for you to go through and do this. To practice your definitions of injectivity and surjectivity. But because of that, this means that it's bijective, and this interval from 0 to 1 is actually in bijection with, or set theoretically isomorphic with the set of all real numbers. And the theorem that we have here that we can show is that this interval, the interval, open interval from 0 to 1, is an uncountable set. And the proof of this that we're going to use is a proof by contradiction. So we start off by assuming that the interval from 0 to 1 is countable, which means that zero or 1 is set theoretically isomorphic to the natural numbers. And this means that we have a bijection from the set of all real numbers from 0 to 1, and then the natural numbers. Which essentially means that we can list out, I shouldn't say all real numbers in the interval from 0 to 1 to the natural numbers. Which means that there exists a function g, which is a bijection from n to r, is that g of I in n will be Ri, or the ith real number in this interval from 0 to 1, and we can go back and forth. And so what this means is that we can effectively list out all of the real numbers in the interval, the open interval from 0 to 1, in an infinite list, where each one of the real numbers in this interval is a countable element, or an element of a countable set. So R0, so the first real number in this set, is in decimal, its exact decimal expansion, D01, D02, D03, D04, and so on and so forth. R1, its unique decimal expansion, is going to be D11, D12, D13, D14, and so on and so forth. R2 in its unique decimal expansion is going to be 0, D21, D22, D23, D24, R3 is going to be 0. D31, D32, D33, and D34, and so on and so forth. And because this is, we're assuming that this set is countable, we can continue this process ad infinitum. And this is going to give us the set of all real numbers in the open interval from 0 to 1. So the idea here is we're doing a proof by contradiction. So if we can somehow contradict ourselves, if we can find a contradictory statement in what we've done, then we've effectively proven the opposite, that 0, 1 is an uncountable set. And sure enough, the way that we do this in the proof is to use what's called Cantor's diagonalization argument, which is a very, very interesting argument. They basically say that if we can construct a new number that is in the open interval from 0 to 1 and not in the previous list, then we have found a contradiction. Because we're assuming that this listing of numbers is coming directly from this bijection between the natural numbers and 0, 1, and contains all of the real numbers in the interval from 0 to 1. So we'll call this new number R star. We just say that R star has a decimal expansion of D1 star, D2 star, D3 star, D4 star, and so on and so forth, where Di star is equal to 4 if the element Di plus 1 is not equal to 4 and is equal to 5 if the element Di plus 1 is equal to 4. And the reason that this is giving us a contradiction is the following. We're going through and looking at each and every element in this countable list on the diagonal all the way to infinity ad infinitum, and we're subtly changing the elements on this diagonal list on every single one of these numbers in this infinite set. we're constructing a new number that cannot be contained in this list because it differs in the I plus first decimal place. This new number, r star, differs in from every single number in this infinite list, and therefore we have a contradiction. So the number r star differs differs in the I decimal place with every number in the preceding list because the preceding list is supposed to be all numbers in the interval from 0 to 1. We have a contradiction. And therefore, we must conclude that the interval from 0 to 1 in the real numbers is uncountable. And so this, combined with the bijection that I went over earlier, shows that the set of all real numbers is uncountable. So to finish the lecture, I'm going to state and show a couple very, very useful results that can be used for investigating the cardinality of sets and really the relationship between the power set of a set to the set itself. The first theorem is known as Cantor's theorem. And this is that it's the following statement. If we let F be a map from the set A to its power set, P of A, set of all subsets, then this function from A to the power set of A is not or cannot be surjective, or is not surjective. And there are no surjective maps from set A to the power set of A, but there are many injective maps from set A to the power set of A. As a consequence, the cardinality of any set A will always be strictly less than the cardinality of the power set of A. And the proof of this is relatively straightforward and uses logic, straight logic from similar to how we use Russell's paradox. We consider the set B defined as a set of X in A such that X is not an element of f of X in the power set. So remember, this map F is going into the power set. And this is a proof by contradiction. Assume that F is surjective, in which case there exists some xi in A such that f of xi is equal to the set P, which by definition has to be an element of the power set of A, because it's a subset of A. And the problem occurs when we think about exactly how we've constructed B. Because by construction, if xi is in B, or is an element of B, then xi is not in f of xi, which is equal to B. And vice versa, if xi is not an element of B, then by definition xi is an element of f of xi, which is B. Right, so we have a contradictory statement. We have that xi is an element of B if and only if xi is not an element of B, which is the statement P if and only if not P, which is a contradictory statement. And because of that, we have to conclude that any function from a set A to the power set of A is not onto. So it can't be surjective. However, it's very easy to show that there does exist an injective function. The simple function G mapping X into the subset containing X is an injective function. So therefore we conclude that the cardinality of A always has to be strictly less than the cardinality of the power set of A. Not only that, but we can go through and show very nicely that the cardinality of the power set of A will always be 2 to the cardinality of A, even for infinite sets. Now, the book proves this for finite sets, but the idea here behind the proof in general, or the proof that the power set of A is set theoretically isomorphic to the function set 2 to the A. Right, from this we have that cardinality of the power set of A is 2 to the cardinality of A. The idea here is that if you think of 2 to the a as the set of all functions fs from a into 0, 1, where fs is what's called the indicator function, so it's 0 if x is not an element of S, and 1 if x is an element of S, and S is a subset of A. This set of functions, right, can be shown to have the same cardinality as the power set, the set of all subsets of A, which is very, very neat. This is one very, very important thing to consider, and it leads us to see a very important relationship. If you think of the cardinality of the real numbers, this can be shown to be the same thing as the cardinality of all functions, from the natural numbers to a binary set, which is the same thing as the cardinality of the power set of the natural numbers. Now, I'm not going to go through and show this. However, to get this result, constructing an explicit bijection between sets is very, very, very not nice to do, not be a nice thing to go about and do. So in order to get this result, to get at this result that these cardinalities are equal, or each one of these sets are set theoretically isomorphic, you use what's called the Schroeder-Bernstein theorem. Sometimes called the Cantor, Schroeder, Bernstein theorem, which says that if A and B are sets, with cardinalities, cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A is equal to the cardinality of B. In other words, you remember that we defined cardinality like this between sets in terms of injective functions. So we have that if there are two injective functions f from A to B, which is injective, and g from B to A, because this is what we need to have these two inequalities with the cardinalities here, then there exists a bijection between the sets A and B. So in the homework for the class, I'm going to have you go over the proof, the written homework. It's kind of long, so I'll have you go through it step by step and kind of take you through the proof of this theorem. It's just one of the proofs of this theorem, but it heavily uses compositions, and it's a very, 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 very interesting and important proof in mathematics. The theorem seems straightforward, but it's a little bit more involved. But what it's basically saying is that if you have two sets that you're trying to show are in bijection with one another, if you can find an injection from one set to the other and vice versa, then this is good enough for showing a bijection between these two sets, which is very, very, very neat. So even though I'm not going to go through and explicitly go through this example in detail because it's a little bit long, we can effectively use the Cantor-Schroeder-Bernstein theorem to find an injection from the set 0, 1 into the set, it's the power set of natural numbers, which is set theoretically isomorphic to a set of functions from the natural numbers to a binary set 0, 1. If you find an injection from this set into this set, and this set into this set, then you have that the two sets are bijective by the Cantor-Schroeder-Bernstein theorem. So this is how you would use this theorem and how it is used to show this relationship, which is very cool. So I'm going to end the lecture by talking a little bit about two important applications and concepts that are very, very important. One a little bit more theoretical, one more applied. The first example is known as the Continuum Hypothesis. Which is a famous open question about cardinality of sets. And like we said that talked about before, we showed that the power set of the natural numbers can be shown by the means of the Schroeder-Bernstein theorem to be set theoretically isomorphic to the set of real numbers. And because this set is also set theoretically isomorphic to the set of all functions from the natural numbers to a binary set, we explicitly have that the cardinality of the real numbers is the same as the cardinality of 2 to the natural number, cardinality of natural numbers. And we know that from Cantor's theorem from before that the cardinality of the natural numbers will always be strictly less than the cardinality of the power set of natural numbers, or the cardinality of the real numbers, which is C. And the idea here is the following. This actually leads us to what's called the Continuum Hypothesis, which asserts the following. There is no cardinal number between the cardinality alpha naught and C, which essentially means the hypothesis that there is no set A such that the cardinality of A is between the cardinality of the natural numbers and the cardinality of the real numbers. Now, this is a very interesting statement because it can be shown that the smallest infinite cardinal numbers form an infinite sequence, elf naught, elf 1, elf 2, and so on and so forth. And if the continuum hypothesis is true, it would follow that elf 1, the next cardinal number, is actually the cardinality of the real numbers, so the cardinality 2 to the elf naught. But what's interesting here is that Cantor stated this hypothesis in 1877, and he labored unsuccessfully his entire life to prove it, becoming extremely dismayed that he couldn't prove it. And by 1900, settling this hypothesis was considered to be among one of the most important unsolved problems in mathematics. But it's still an open question to this day, and it remains an area for active research. But what has been shown is that this hypothesis can neither be proved nor disproved within the confines of ZFC set theory. So it's kind of outside the modern ZFC set theories or Miller-Frankel axioms. And so there's a lot of controversy over whether or not these axioms should be replaced by some other set of axioms for set theory. Because of this. However, this is still an open, very important problem. And the next example that's food for thought, it's a good thing to think about, is the definition of a computable function. So we can actually define and say that a function is computable if there is a computer program in some programming language that can find the values of this function. And likewise, if a function is not computable, then we say it's uncomputable. And to show that there are, in fact, uncomputable functions, we can do this by establishing first two results. First, we need to show that the set of all computer programs in any particular programming language is countable, which can be proved by noting that a computer program in a particular language can be thought of as a string of characters from a finite alphabet. And then after that, we can show that there are uncountably many different functions from a particular countably infinite set to itself. And this is done in some of the exercises at the very end of this chapter in the book. But in particular, in one of these exercises, we show that the set of functions from the set of positive integers to itself is uncountable, which is then by consequence of the uncountability of the real numbers from 0 to 1. And if we put these two results together, we have that there are uncomputable functions, which is a very, very interesting application of some of the ideas that we've been talking about in this lecture. But that will conclude the lecture for today. Thank you very much for tuning in. I hope you learned something and had a fantastic day. So I want to make